Alright, this is 6.5, 363 in your textbook. We're describing situations from graphs. So it's similar to the last example, just going into a little bit more detail with the actual problem and the variations of different graphs we can get. The first one we look at is Bill's trip. So we notice that we're measuring distance versus time. Okay, so this is distance from his house. So if the distance from his house is starting at point A is 0, that means he's at home starting at point A. Okay, so as he starts to move away from home, the distance from his house increases. So in the first 4 minutes, he moves from 0 meters to 200 meters. Okay, so one of the things we can do when we have a distance versus time graph, if we take the slope, we know the slope is distance over time. Okay, distance over time, another way of expressing that is just to call it the speed, right? Just like we have a speed limit on a highway, so many kilometers per hour, distance over time is speed. Okay, you guys should be familiar with that equation as well. I think there's that triangle. It looks like that. You might have learned from science class. All right, so distance, speed is equal to distance over time, distance is equal to speed times time, and time is equal to distance over speed. All right. Okay, so what we find out then is as he moves further away from his home, so now when he's moving from 200 meters to 400 meters, again, moving a total distance of 200 meters, it actually takes him a little bit longer. It takes him 8 minutes, from 4 to 12. So you can see, again, by the slope, that he's slowing down a little bit. All right? So we see here he sets out at a certain speed, which is the slope of this, and we can see that the slope of this line now is less, as we can see that decrease in speed. Okay? And then back when he goes from C to D, again, he's traveling 200 meters. He goes back to the same speed he was traveling at from A to B. All right, so he takes off from his home at a certain rate. He gets a little tired, goes slower, and then he speeds back up. Okay, from 12 to 20 minutes. Okay, and then this is the point at which he arrives at the store. Okay, so there's a period of time where he doesn't get any further away from his house. So he's inside the store at this point. Doesn't mean that he's not moving back and forth inside the store, but his actual distance from home is not changing. Okay, so he's not getting further away from home at this point. He's at 600 meters away from his house. Okay, and he stays in the store for approximately 8 minutes. Okay, so that's why we have no slope there, because his speed is 0 in relation to his distance from his home. Okay, so he's not moving further away from the home. Okay, then he starts to return home. Starts off very slowly. Okay, so from E to F, he's going at a much slower rate than he was when he was leaving his home. So he's heading back towards his home because the distance to his house is getting lower, so this is him getting closer to home. But he starts off at a much slower rate, as you can tell by that slope being very gradual. And then when he gets to F, he speeds up and heads home at the same rate that he left originally. Okay, so even though the line is longer, the slope is the same. So he's just traveling for a longer amount of time at that same speed. Any questions?
Sir, isn't that line steeper?
Sorry?
Isn't the F to G line steeper?
Yeah, but it might have like graphed.
It looks very close. 1, 2, 3, 4 over 1, 1, 3.
Very close. I think this might be actually a little steeper.
Yeah, A to B.
Yeah, A to B. It's very close though. All right, so did Bill make it home in 30 minutes? So how would we answer that?
No.
You can tell me. Mark, did he make it home in 30 minutes?
No, because he passed the 30-minute.
Right, so 30 minutes was right around here. We can still see that he's quite a fair distance away from home. Okay, so we find out he actually made it home right around 40 minutes. Okay, so he wasn't quite home yet. Any questions about this graph? How it works? All right, calculate the slope of each line segment. So again, to calculate the slope, we get those 2 points and we use m is equal to y2 minus y1 over x2 minus x1. So you need to be familiar with how to do that. Yeah.
Would there be a table of values to tell us coordinate points?
No, you would read the coordinate points from the graph. Okay? All right, looking at example 2. So in this example, we have a skydive for jumping from an airplane. And then we have the height. So this is height meters above the ground. So starting at 6,000 meters up in the air. And then this is the time from when they leave the airplane. Okay? So what we notice is that obviously as we get closer to the ground, the height is getting lower. But we also notice that it starts to speed up. Okay, so obviously when we first jump out of the airplane, our relation from our height to the ground to our time is 0, and then as we start to fall out of the airplane, we're picking up speed. Okay, that's why we start to drop quite a bit quicker. All right, so this relationship, how would we describe it? You can tell me. Linear or non-linear? Josh?
It's the curve of best fit.
Right, so we have a good, so there's a curve of best fit. Good, that's part of it. And, Kevin?
For non-linear ratio.
And it's non-linear, good. Okay, what I want to point out with this particular example, we do have, again, we're measuring distance and time, so the slope of this graph would be your speed, okay? But because it's not a straight line, your speed is changing, okay? So the slope of these 2 points would look like that. The slope of these 2 points would look like that, okay? And the slope of these 2 points would look like this, okay? So because your slope is changing, your speed is changing. Okay, it's not constant. It's not linear, so the speed or the slope is not constant, so your speed is changing. What do we call that when speed changes? Yeah.
Acceleration.
Good. So we're accelerating here. Very good. Accelerating. Okay, so that's what I wanted to point out with this particular graph. You can tell from the graph that this individual is accelerating as the time increases from when he jumps out of the airplane. Any questions? Okay, good. All right, last example here. We have 3 different containers, and it says match the graph with the container being filled. So we have a tap up here, and the tap is filling each one of these containers. And what the graph shows us is the depth of the water in relation to the time being filled. So as the water flows into these containers, the depth is obviously increasing as time is passing by. Okay? So that's the whole idea of this section, is trying to go from a graph and trying to visualize what is actually happening in reality. Okay? So here are our 3 containers. So what we want to think about is, as this container fills up, we can see that as it starts to fill up, it's going to fill up much slower here as it will on the neck, right? Because if we're letting water go at the same rate, as we get to the neck, this is going to speed up, right? That's going to fill up much quicker, the neck, right? If we've ever filled up a bottle, we know that as we get closer to the top, because this diameter gets smaller and smaller, it fills up very quickly. So we should be able to realize that for this shape, the change in depth with relation to time is not going to be constant. Okay, it's going to change. Not only will it change in this triangle area, because again, the diameter of this is changing as we go up, but it's going to change drastically when we get to this point, the neck, because then it's going to get really thin. Yep.
It would be B.
Yeah, exactly. Right. It's going to be B, because we know that the depth is not constant. It's going to increase the rate at which this object is filling up. Okay, so that's why this particular object is this particular graph. Okay, because as time goes on, the depth of the water, as we get closer to the top, it's going to really speed up and take off. That's why we get that kind of increasing in depth. So that leaves these 2. Both of them are cylinders. Okay, so they both have the exact same shape. They both have a constant cross section. There's no change. There's no change in these. The rate at which it's going to fill up is going to be constant because the diameter doesn't change. So the only question is then, we know they're both going to be straight lines. The only question is then which straight line goes with each shape? And Michael. Yeah, you.
For the second one, it would be C, because it would go,
This one would be C. Why is that?
no, that one.
The second.
Oh, sorry. This one is C. Yeah, why?
Because it would fill up at a slower rate.
Right, because the diameter is much greater, the depth is going to take longer to fill up. Okay, so that's right. So this is going to go with A. You guys understand that?
Yeah.
Any questions there? All right, moving on. In summary, so our velocity or our speed, which we call V, is equal to our change in distance over our time. That's from a distance time graph. The slope of distance time graph is speed. In a linear relationship, speed is constant, and in a nonlinear relationship, the velocity changes with time. Okay, in other words, speed is not constant. Speed is not constant. And there is acceleration. Okay, any questions with this? All right, that's the end of the lesson.